All right, thanks a lot. Hey, everyone. Thanks for tuning in. It's great to be back at Scale by the Bay. I think 15 is a round number. Maybe it's not quite 15, but hopefully that doesn't matter too much. I will post the slides for the conference later, and I'll have them on my personal website later as well, but they're not up there yet. Just a little bit about the photos. If you've ever seen my talks, I like to put in photos from trips, backpacking, and so forth. This happens to be a road in Nevada. Actually, all these photos are from Nevada. And you can barely make out a little dust devil under the D in wild, just barely. I don't know if you can really see it, but there's a little dust devil out there. I work for Domino Data Lab, which is actually a heavy user of Scala. It's basically an integrated platform for data scientists that help them manage their work. Sort of like the way we use IntelliJ to kind of integrate everything together so we don't have to think about a lot of details for managing our assets and so forth. So check us out if you're into data science or data engineering, helping data scientists. We are hiring. We've got a lot of openings for Scala, Kubernetes, even Go, and that kind of expertise. So please check us out. DominoDataLab.com. It's not Domino Pizza, anyway. Yeah, I finished the 3rd edition of Programming Scala. I think it was early this year, actually. I'm kind of losing track now. You can find out a little bit more at programming-scala.com. That's a personal website. And I'm going to show a little bit of Scala 3 syntax and talk about why I think it's kind of a great evolution of the language, addressing a lot of the things we've learned over this last, really Scala's basically about 20 years old now. But obviously can't go into a lot of detail, so please check out the book if you want more. Actually, there's also some other reference information at this website that goes into a little more depth than I can have time to go into today. So first, let's talk about how Scala's evolved a little bit, and in response to what we've learned about how to use it effectively. I'm going to talk about these 3 points: greater clarity. Moving from the concept of implicits to a sort of a refactoring of it to context-based abstractions, and then talk about a few of the improvements in the type system. And I noticed earlier that M is cut off, and I forgot to fix it. So maybe you didn't notice until I pointed it out. Anyway. And then I want to talk a little bit about enterprise Scala and some of the ways in which I think it really has rejuvenated, at least for me, the life as an enterprise application developer, and some of the specific things that are maybe hot button issues for me. I'll vent a little bit if I'm allowed to do that. I'm sure that'll be appreciated by some of you. So let's first talk about greater clarity, how Scala is helping us have code that actually it represents the intent that we're trying to write, is more concise, even though Scala has already been famous for being concise, and how it's become even more concise in Scala 3 and so forth. And I'm going to start with one of the more controversial choices that was made in Scala, which was to actually Scala 3, that is, which was to introduce an option to use no braces, more like a very Python-esque kind of syntax. So on the left, I have what may be familiar to you if you've worked with Scala before, or Java, maybe where you use braces to mark off blocks. Here I'm declaring a trait for a monoid. All right, we're talking Scala, so we always have to get into like category theory concepts or whatever. A monoid is just a generalization of the notion of like addition or multiplication, where I have a 0 and I have some way to add 2 things together. I'll actually show you a good example, a slightly more sophisticated example shortly. But the point being here, notice the differences from the left to the right. On the right-hand side, we use a colon to mark the end of the name of the class or trait in this case, and then indentation to indicate methods. And then inside the methods, they would be further indented. We'll see that as well. I also threw in one example of what pattern matching looks like. When I heard about this idea, I really thought, we don't need this. Why is this being introduced? It's yet another difference, but I've actually really come to love it. I used the syntax almost exclusively in the book, and found that I just really like the way it makes things concise. And one of the interesting ways it makes things concise, besides just getting rid of a little punctuation, is, if you've ever written like Python or any of the languages that use indentation style syntax, you realize that you can get lost pretty quickly. There is actually a mechanism in Scala to deal with like marking the end of a block, but I think also it kind of really encourages us to be concise, to write concise methods, to extract methods rather than have lots of nested code and so forth. So I really like the cleanliness that this introduces. And you could call this Python X syntax in Scala 3 if you like. The other thing that's happening is this notion of more intentional constructs. And this is the idea that, you know, if we're actually want to be able to reopen a type and add methods to it, the way we've done it in the past is shown on the left, which was implicit type conversions. And I'm actually showing you the exact definition of the arrow source object or class that's in the standard library, which was a way of being able to write like A arrow B and get a tuple back. And if you've ever written any of these yourself, you get kind of used to how you idiomatically use this mechanism called implicits to define this. But if you step back and put on like, you know, the beginner's mindset or whatever, beginner's eyes, it becomes completely unobvious what's going on here. And yet it's a very powerful mechanism. So Scala 3 actually introduced true extension methods where you just say extension for some type A in this case, and here we want it to be flexible for any type. And we're going to define, I use tilde arrow just to be different than the regular arrow. And then we just define the method that we want to exist on this type A, whatever A happens to be. And then we take an argument for the B that returns then a tuple. Target named is an interesting little feature that's new too. This is actually the name that will appear in the bytecode that's generated. You can't call this method arrow2 or use it with that name. You have to use the tilde greater than sign. But if you were calling this from Java, you could actually invoke this method using arrow2, it turns out. So that's what the target name is all about. But couple things also, not only is it more intentional, it's really saying exactly what we want to do, which is open up this class and add a method to it, but it's much more concise, which is really nice. To be fair, there's, I put in the full definition on the left, so there is the second version of the method that uses the Unicode character that has been deprecated. So maybe if I took that out, it wouldn't be quite as dramatic a difference, but it does kind of add up over time. You get a much more concise experience using this new mechanism. And that leads us into some general changes that have been made to make implicits both more intentional about what it is you're actually trying to do, as opposed to having a general mechanism that is very flexible, but requires you to master the idiosyncrasies of how to use it. And the other thing that these changes reflect is thinking about how people have overused implicits. They're very much like a very powerful weapon that you can either use effectively or do a lot of damage. And so there's been some movement towards making it more deliberate in how we use these things for known good patterns and de-emphasizing patterns of use that really aren't as good. So here's that monoid example again, but maybe made a little bit more sophisticated, where I'm going to start with the thing that's called a semi-group, and all that is the generalization of this sort of addition operator, and then monoid just adds the notion of a unit or a zero or something. But just walking through a little bit more on the details here, there's a couple of interesting things going on. In the trait, what we're going to do is use this to add extension methods. That's the only way we're going to use this semi-group. So we're going to define some combine method that is currently undefined, it's abstract, and then it will have to be instantiated for integers, strings, etc. And also we're going to define this operator syntax, with I use the sort of the Darth Vader spaceship kind of operator for plus in this case. You'll also notice a new keyword, infix. This actually tells the compiler inline this method. Do not make an actual method call. And it turns out this is a really powerful tool also in combination with the brand new macro system. So you can get extremely performant code that is where things are decided at compile time and then a lot of code can be inlined. Obviously you can abuse a mechanism like this, but it's a really nice tool for keeping your code concise as well. But notice that the combine and I'll just call it the plus operator are both going to be extension methods. But when we get to monoid, notice that unit is not an extension method. And that's because we only need like a 1 unit per type. You know, the 0 for integers is going to be the same for all instances of the monoid. So this is actually basically going to become an object method called the monoid unit for each of the instantiations for type T. So again, implicits are a mechanism that is very powerful, but you had to understand the idiomatic ways to use it. And what we're trying to get to is something that's more intentional. And we're also going to talk about the notion of how you pass what used to be called implicit arguments. They're now called using clauses, and the givens are the implicit values that are in scope. So if we want a string monoid, we declare it with this syntax, given string monoid, and this is the type declaration, that is going to be an instantiation of monoid with the definitions that we need for strings. So the unit string is an empty string, obviously, and then we define the extension method. You have to have all these keywords that you're seeing that even though they were already, given, if you will, in the original definition. And for strings, we can actually use the plus, the real plus operator, which is a bit of a cheat, but that was kind of a convenience that is in Scala and Java and other languages. And then if you use this, in a shell environment or whatever, it behaves exactly like you would expect. A lot of the usual algebraic properties of addition are satisfied. That's shown in the first example here. And then if I add to the unit, and notice how I'm referencing it as like an object member. If I add 1 to string monoid unit or reverse the order, then I get 1 back. So it kind of behaves exactly like we would expect. And a kind of a fun one is to define, I think, let's see, this is not working. There we go. I hit it. Couldn't get the build to work. For numeric monoid, we could define monoid instances for, int, double, et cetera, but we can also use numeric. And this is how you can do things like type parameters in the usual way. So this will work for any kind of numeric type. Notice the function called summon. That's the new version of implicitly. So it basically behaves exactly the same, but they just defined a new function with a new name. So we're going to summon the in scope context for a numeric of type T, and then we'll grab the 0 value from that. That's how we define the unit here in this case. And then with the extension method, we also need to summon the numeric instance in scope so that we can call the plus method. And now if we can do this with that one definition, we can do addition with integers, doubles, big ints, and so forth, just kind of like the previous example. I'm going to come back to this point a little bit later, but obviously one of the things that we Scala developers end up doing is learning to master type parameterization and how to use types effectively. And the power comes into play when you see something like this, where with 5 lines of definition on the left, I now have something that applies to a wide class of types. And I could even add support for my own custom types if I define a numeric equivalent for them. So these are the kind of things that really, really pay a lot of dividends and lead to a code reduction, even though maybe the sophistication increases. And that has major implications for enterprise development, as I'll discuss at the end. Just checking my time here. So just to complete the thought here, what about passing arguments like context parameters, where we used to say, it's an implicit argument list. Now it's going to be a using clause. So I just sort of sketched out the idea. I'm going to pass some context. I'm going to declare a trait and then do another given to create an instance of it. And then I have some method that's going to do some processing where I pass in a string and then a using clause that takes one of these context objects, and it's going to summon the value again and return a string. So it's kind of a silly little example, but the point being that I can get the benefits I've enjoyed in the past of using implicit argument lists when I call process, as in this example. But there are some things I'm glossing over that are advantages. It turns out if I wanted to explicitly pass that context argument, I would have to add a parameter list that begins with using as the keyword on this right-hand example. I can't just pass the value what that does for us is that when we see this in code, it very unambiguously indicates that something is being passed explicitly, even though it's an implicit argument. So that's kind of a cool way of removing some ambiguities. Okay, there have been a bunch of improvements to the type system, both to make it more sound and also to make it a little bit more convenient to use in a number of ways, and even to address some pragmatic issues like performance. And that's the first one I'm going to talk about. I'm not going to survey all the changes, they're huge, but just to give you a taste of some of the cool things that have been done. One of them is a new idea called opaque type aliases. And here's an example. I think I stole this from the Scala documentation, of a way of defining logarithms in a way that doesn't add any overhead over what double has an overhead. In other words, there won't be an allocation for logarithms. There'll just be a double in the bytecode. And the idiom that you follow, or I guess the practice is you declare this opaque type, logarithm in this case, you declare some methods for constructing instances of them, and I show two here. One is that we just assume that the double passed in can be converted to a logarithm. That method math log is not defined for all doubles. I think it's at 0, it blows up, if I remember my math correctly. But we also have a safe version that, anything 0 or less, any number that's valid has to be positive. That's the way I want to put it. So the safe method actually does a check, and it only attempts to create a logarithm if it's a valid value, and then it returns an option. So that's our constructor methods, or equivalents thereof. It's sort of the analog of the usual apply methods. And then if you want any methods, you have to define them as extension methods. You don't automatically get all the methods available on double. So here I define 3. One to extract the double, and notice we do the exponentiation of it to get it back to the original double, and then plus and multiplication. So that's a cool way that affixes some of the limitations of previous mechanisms for like the any val types, that lets us get the performance of doubles while still getting the convenience of sort of an object-oriented notation like logarithm. One of the cool things that everyone's been talking about is intersection and union types, and these are the last two that I'll mention in talking about type systems. Intersection is really sort of what we've been using all along with like if you define something that can be reset, so it has a reset method, or I can grow it, it's like an extended, add new things to it. Then we would, a type would be something like X is of type resettable with growable. That's typically how we would do it. But what this actually changes is a couple of things. One is that those types now commute. So something of type resettable and growable, notice the ampersand, is also type compatible with growable and resettable. Now there's some subtleties about this, that it's not completely compatible in the same sort of sense. But I really don't have time to show you some of these subtle differences, and it mostly has to do with deciding which methods to call in a type hierarchy. That actually is still dependent on the order of declaration. But what it does allow us to do is to pass arguments that are of type resettable and of type growable. So if you think about a Venn diagram of all the instances of resettable, all the instances of growable, there's some subset where they overlap, and those are the only allowed values that you can pass to this, because I'm calling both methods in this case, in this example. So that's a more concise way of dealing with these kind of intersections of types. The other one is unions of types. So this is a way of extending kind of the idea of what we use either for, either left or right. To be either an arbitrary number of types, but you don't get the same sort of monadic behavior with this, but sometimes this can be a very useful thing. So notice what's happening here. I've declared some case class to represent users, and I'm going to get a user from a database, and the return is either going to be a string, which will represent an error in my case, or I'll return a single user, or I'll return a sequence of users. And the way you have to work with these things is actually using pattern matching, because you don't know what the type is when you call in. So what I'm doing here is I'm sort of mocking out the idea that I'm going to run a database query where I'm going to select all the users where ID equals something. Maybe that's not a unique single record. So I'll look at the size of the result set, and if it's 0, then I'll just return that string, which is my first option, which is an error message. If it's 1, then I'll just return, I'll assume that the result set is like a sequence, whatever it is, but then I'll just return the first element, and maybe I have some conversion that converts it to a user type, is what I'm mocking out here, if you will. Otherwise, I'll just map the sequence to a sequence of users, whatever the result type is that comes back. But notice that pattern matching has to be used here. In this case, it has to be used to make sure I return the right instances of something. More interestingly, though, is at the bottom, where I use pattern matching to analyze the result of calling get user. So I immediately do a match on it, and then is it a string, is it a single user, or is it a sequence of user, and then handle those 3 cases separately. That's the only way I can do it. You could do things like as instance or is instance of, which is of course not the way we normally do things. But if you're using union types like this, then you usually use pattern matching to figure out what you actually got. Okay, in my remaining time, I'm going to talk a little bit about sort of at a larger perspective, if you will, of where things have gone right, where they need to go better in Scala, and how we use it, and how we can, I wanted to be very direct about this subtitle. How can we unlearn enterprise Java habits that I think often drag us down, even when we're writing code in Scala? And I speak from years of experience working in various Scala projects. And I'll just talk about 3 areas. Obviously, most of you that are watching this talk are probably already either into Scala or into functional programming. Maybe you're using another language, and you may believe that OOP is object-oriented programming is garbage. I don't believe that personally. I think Scala does a really good job leveraging the best strengths of both, but I really do try to emphasize functional programming in the following senses. One of the sort of mental exercises I often go through when I'm starting a new use case or user story or whatever it is I'm implementing is I like to think, if it's sort of data-centric, what would a SQL query look like that would implement the whole thing? Could I write a SQL query that could actually do this whole thing without all of this Scala, Java, whatever code I normally write? Because it's hard to imagine anything more concise than a SQL query. Now, if it's more like a process that I'm building, then I often think of it in terms of like a bash script, which for me is kind of, about as concise as sort of a procedural kind of problem can be written. But, when I think about something like this, a trivial query here, then, everything else is kind of boilerplate in a sense. I mean, I do need things like security and, failover and logging and all that stuff. But a lot of the problems I see in code bases today is really forgetting how concise things can be and adding a lot of unnecessary ceremony, or not knowing where to cleanly separate the business logic from the required ceremony that wraps around it. The other thing that I think is very important is parametric polymorphism. I wish I had a little more time to talk about this. This is a blog post I wrote where I talked about its virtues, but I actually talked about it as a way of drastically reducing code boilerplate, and not so much about what I'm talking about on this slide, although I mention it at the end. What this slide is about here is, if you look at the signatures of these 2 functions and you ask yourself, I can't see the body of these functions. The names don't mean anything, obviously. What are all the possible implementations that could exist for these 2 functions? And if you think hard enough about the first one, it turns out the only reasonable assumption is, because T could be anything, this has to be the length method or size. There's really no other reasonable choice I could make. And what's beautiful about that, if you look at languages like Idris, more advanced functional languages, they can actually generate the code for a signature like this, because they can very precisely determine the only allowed choices, and they can generate tests for it or whatever as well. Whereas if you think about the second example, the paradox here is I'm being more specific about the type that is coming in, but I'm actually losing a lot of this sort of reasoning power about possible implementations. This could be the first element, the last element, the median value. There's all kinds of possible implementations that would satisfy, in some reasonable sense, what this signature is, as well as the size method. So the paradox again is, by making the type more flexible, I actually constrain the allowed choices of implementation, and that actually gives me a lot more precision and avoids a lot of ambiguities that are possible. So I really like to think about, how can I use my types to set the proper boundaries of what this should be able to do. Here's something I've been wrestling with a lot. I don't necessarily have the right answer for it, but when should we really faithfully, statically, strongly type everything that we work with? And the example I'm wrestling with at the moment is, we work a lot with Kubernetes at Domino, so I just grabbed this sample YAML from this Kubernetes website. And it's very tempting, we do this a lot in the enterprise JVM world, to have exactly this schema represented in code, because we're going to stuff in values for some of these fields, and then we're going to spit out YAML. So we've got also this ceremonial code for reading and parsing YAML and generating YAML from a map or whatever data structures we've declared. And it really does seem like a total waste of time to me. So one of the things I've been thinking about a lot lately is, maybe we should be reading templates of these files, and ironically, the word template happens to be in this YAML example. But we should have kind of the way we do interpolated strings. Let's just load this in and have the minimally sufficient information in the code itself, and not have to know about everything. Because as soon as we change the schema, a new version like V2 of this API comes out, then we end up modifying code that maybe doesn't really change anything that it does of use. So I'm really thinking about ways in which stuff like this ought to be either replaced with maps, where we don't worry about the types, we just treat them as strings, or cases where we just have the minimal amount of type information for the business domain, and the rest passes through as data instead of code. So anyway, something I'm thinking a lot about. The last point is that if we apply all of these methods, all of these lessons that we've learned, then we get a lot less code, and that has enormous benefits for us. Here is a complete Spark program. This is taken from a talk I did maybe 5 years ago. It does the inverted index calculation. That's not important for our discussion. Well, I highlighted all the methods in yellow here, and those of you that write Scala, these are all friends, right? Map, flat map, filter, reduce by. Reduce by key is I think just an extended method in the Spark API. Nevertheless, if this is the whole program, then do I really need a lot of the other stuff that we typically pile into our environments? Do I need a dependency injection framework of some kind? Do I need fancy mocking libraries for my tests because my dependencies are out of control, because I used a dependency injection framework to let me avoid solving the problem of my bad dependencies? Do I need a lot of the design patterns like factories and adapters and so forth? A lot of functional people sort of like to badmouth design patterns. I actually think they're a great idea. It's always whether they're used properly or even necessary that's really the issue. And then if we don't have a lot of code, maybe we don't need as many microservices, except for just failover or scaling. And maybe we don't need to split things up, because our domain has become less complex as a result of just focusing on the core abstractions of the domain that we have to implement in code, and let the rest be data. So anyway, that's my view on views, if you will, on how Scala has made me a much better programmer, but we've still got a long ways to go to make enterprise JVM development as optimal as it can be. The links here, my Twitter profile is Dean Wampler. You'll be able to get this talk from the conference website and from my website probably later tonight. And then I also, my blog is on Medium now, and do check out Domino Data Lab. Thanks.